Good morning. Okay. The first speaker of this morning session is Juan Barranco. He will talk about the same. Yeah, it's different. Okay. I'm very the nature thing.
Okay, so. Okay, thank you, sorry. So, essentially what we want what I would like to talk with you is about if we understand what is the neutrino nature. I'm by nature, so I went to the dictionary, and then I went to, and this is the definition of nature, so this is the inherent character or basic constitution of a person or thing. So essentially what we would like to know is what are the inherent character of the neutrino. So probably by an enumeration of its properties, a description of its interactions. So what is the neutrino properties? The story about the neutrino nature is a little bit complicated. This is it started with its birthday. So actually it is of the few particles that has a certificate, it is this one. It is a letter done by Pauli where it was officially born, the neutrino. Since I don't know German, there is a translation of this letter. So as you already know, neutrino was introduced to solve a problem, and the problem was do we stay with the conservation of energy, or we have to do something? And Pauli suggested to introduce a particle. At that time he called neutrons, which has a 1/2 spin, so it is a fermion. It has a mass. At that moment he was thinking something as small as the mass of the electron. So at that moment the neutrino, the properties of the neutrino, at the very beginning, at its birthday, the neutrino was a fermion with no electric charge and a very small mass. Of course, after its birthday, Pauli was terrified because he said that he had done a terrible thing. He has postulated a particle that cannot be detected. But as in many cases, when we try to understand our nature, most of our issues are coming from our parents. So this is the case of Pauli. But just start to grow up, and then the neutrino grown up. So you know, particles where the neutrino was discovered by Reines in 1957. Then neutral currents were discovered, and so on. So among 50 years, the neutrino grew up and become the standard model neutrino before Snow Lab. So at that moment, we can think that the neutrino, the properties of the neutrino was, he has no electric charge. At that moment, it has no mass, and the reason why it doesn't matter the mass for high energy physics is because in most of the processes in high energy physics, the correction, if you include the neutrino mass, will go as the energy of the process divided by the mass of the, in the opposite way. The mass of the particle divided by the energy of the relevant process that you are considering. So if you are working for lead, the energies are of the order of giga-electron volts, so the corrections will be very small, so it doesn't matter at high energies if the neutrino has mass or no. But for the standard model purposes, so it is nice to have a neutrino with no mass. So we knew that it comes from three flavors. It is left-handed, it has no magnetic field, no magnetic moment, and it is a fermion. So this is the idea we have for the neutrino. But as we were discussing yesterday in the lunch, we know quantum mechanics, and essentially a process that appears, so a quantum mechanic, what is the difference between a process that you have to study with quantum mechanics and a process that you have to study with classical physics? Essentially, it is determined by the uncertainty principle. So essentially you have a particle that travels some distance of this magnitude delta x, and it has a associated momentum delta p. So it is relevant for quantum mechanics as long as this product is of the order of h bar. So if this product is very, very big, you can forget about quantum mechanics. It is just a classical process, and then Newton's law applies. But if this magnitude is of the order of h bar, so quantum mechanics is irrelevant. So neutrino oscillations are a poor quantum mechanical effect. So imagine that the neutrino, you postulate the neutrino is a massive particle, but you have to add something extra, and this extra is that its flavor basis is different from the mass basis, and then you have a mixing between these two bases, and then you can compute what is the probability of going from one flavor to other flavor, and this in vacuum for two flavors it is given by this. So oscillations are relevant as long as this product, which essentially is this delta p times delta x, so the distance and the momentums are of the order of h bar. So oscillations are really a quantum mechanical process. And then if we were discussing yesterday, kind of funny that if you want to look for a macroscopic effect of quantum mechanics on some quantum mechanical effect that appears in a kilometer size object, it is neutrino oscillations. So neutrino oscillations were introduced in order to solve among other problems, with the neutrino solar problem. Essentially the problem is that the prediction of neutrinos is very different from the one that you were detected. You construct very different detectors. In all of them, you observe this discrepancy, except at the moment when you construct a detector where that is sensitive to the three flavors, and then if you measure the three flavors of the neutrinos, you realize that the neutrinos coming from the sun arrive to the Earth. So originally, all the neutrinos coming from the sun are electron neutrinos, but along it's traveling from the sun to the Earth, they oscillate to different flavors. If you construct a detector that is able to detect all flavors, you recover essentially the predictions of the number of events that you were expecting. You have a consistent picture, not only for the solar neutrino problem, but for atmospheric neutrinos, where you now have introduced new properties for the neutrino. So the new character of the neutrino is that still is it has no electric charge, it has mass, and actually the mass basis is different from the flavor basis, and it is related by a unitary transformation. It has mass because in every case, if delta m squared is 0, you don't have a probability of oscillations, but you need then to measure these values, so you have mixing and masses of the neutrino. Still you have three flavors, it is left-handed. Since now the neutrino has mass, then there is the possibility that the neutrino may have a magnetic moment. The prediction for the standard model for the magnetic moment is proportional to the mass of the neutrino, so it should be very small. Unfortunately, we have a very small, very crude bonds on the neutrino magnetic moment, which are order of magnitude away from the standard model prediction. So at this moment, this is our properties of the neutrino. This is the nature of the neutrino that we have, but we can ask for more. And maybe we can start asking if the neutrino really interacts as the standard model predicts. And the answer is we don't know. So you can start with the standard model Lagrangian, so go to the low energy limit, and then you have an effective Lagrangian for the neutrino interactions. So suppose that you have an extra contribution to this Lagrangian coming from deviation from the interaction of the neutrino with the matter that can be parameterized in a Lagrangian with this structure, which is very essentially is the same structure as the standard model Lagrangian, but you have parameterized all your ignorance of the models here in these effective parameters that are known as non-standard interaction parameters. And then you can take all the neutrino data in order to know what are the values of these parameters that can cover a huge variety of different models in extension of the standard model, because essentially most of the extensions that you can imagine of the standard model, when you go to the low energy limited, you will arrive to a point-like interaction, like the Fermi point interaction, and then all these interactions can be parameterized in this way. So this is a clever way of putting all the new physics, and since as we already discussed, the neutrino oscillations and the neutrino phenomena is a low energy phenomena, then the effective Lagrangian captures all this information, because all this is encapsulated in these epsilons. But okay, so you take all the data, neutrino electron scattering, information from LEP, from the annihilation of electron positron to neutrino, antineutrino plus photons and so on, and then try to find what are the possible values of this epsilon. So essentially what you were expecting is that these values should be small, but nevertheless the neutrino is a very clean process. The neutrino interactions are very clean processes, but the uncertainties we have are big. So the values that you can have from this for this epsilon, so here we try to put all this together. So if you consider, for instance, no flavor changing interaction, so you have the same indices here. So you can have a neutrino electron that interacts, for instance, with an electron and an electron. So you can see that this parameter, for the case of the electrons, are of the order of 10, 20%, 15%. In the case of the muon, it is below the 1%. But in the case of the tau, it can be as big as 1/2. So essentially, you can have new physics phenomena of the same order of magnitude as the standard model interactions. So we don't know at this moment what is the possible values of this. So something that we should start thinking is how to use the recent data from all the oscillation experiments, together with the observation, for instance, of the coherent neutrino scattering, combined with the information that we have from the old data that we have from LEP, for instance, and in combination with the upgrades we will have for superchemicande, T2K, etc., in order to really constrain these non-standard interactions. So why we should bother about these possible new physics coefficients? So the reason is that if these non-standard interactions coefficients are big, it cannot help, it confuses us about other properties of the neutrino. For instance, if these non-standard interactions are as big as 30%, which is the case, for instance, for the case of the tau, then you cannot distinguish if you have a genuine CPU relations in the electronic sector, or it is an indication of new physics coming from a Lagrangian that can be parameterized in this way. So it is really important for the determination of the neutrino nature to really constrain these non-standard interaction parameters. We don't know what is the absolute value of the neutrino mass. So although we know that neutrino is massive, we don't know what is the absolute value. Probably cosmology for now is the best way to look for these absolute values. Nevertheless, cosmology will be model dependent determination, plus the limits will be arise only as a combination of the different mass favors. So this is an open question, we don't know. So, and a very important question we have is, we don't know if the neutrino is a fermion that is a Dirac or a Majorana particle. So in what follows, my objective is to try to convince the people from Borexino that it is possible, if a supernova explodes nearby, it is possible that with Borexino will tell us if the neutrinos are Dirac or Majorana. In order to do that, the objective is to show that the neutrino electron scatterings with polarized neutrinos are different in the case of Dirac and Majorana case. So once I hope I will convince you that this is the case, use this fact in order to see if we can constrain the neutrino magnetic moment, and then after that, in a more speculative way, I will try to comment that possible observation of astrophysical neutrinos coming from supernova may have some difference if they are Dirac or Majorana. So, what should be relevant to distinguish if the neutrinos are Dirac or Majorana? So essentially, it goes to the very fundamentals of the quantum field theory, because in the case of a particle that it is a Majorana particle, the dynamical equation is different. So all the standard model particles are Dirac particles. It will be very strange for us that another particle within the standard model has a different behavior as the rest of the particles in the standard model. So opening a new window from the very fundamentals of the quantum field theory. In the case of a particle that is a Majorana particle, it is equivalent to its own antiparticle, so the neutrino will be its own antiparticle. And because of this reason, if a particle is its own antiparticle, then processes that are not allowed in the standard model can appear. So one of these, the prototype of this kind of experiment is the neutrinoless double beta decay, which will appear in the case that the neutrino is a Majorana particle. So we like this Lagrangian, the Lagrangian for the low energy limit of the standard model, neutral current interactions, and then essentially at low energies the effective Lagrangian for the neutrino electron scattering can be for the neutrino electron interaction can be written in this way. But if you consider the neutrino as a Majorana particle, then it is the spinor, it is equal to the conjugate of the spinor, so it is the definition of a Majorana particle, and because of that you will have, if the particle is a Majorana particle, you will have this identity. So if you compute what is the amplitude for the dispersion of the neutrino interacting with an electron, in the case of the Dirac particles, the amplitude goes like this, and in the case of a Majorana particle, it goes like this. So actually, you can already from these amplitudes see that they are different. In this case, you will have a vector axial term in the amplitude. Meanwhile, in the Majorana case, you will have only the axial part of the amplitude. So from the very beginning, you may think, why, if the amplitudes are different, we have detected neutrinos and antineutrinos by neutrino electron scattering in our experiments, and they are different. How is possible? An antineutrino is different from a neutrino in the neutrino electron scattering. Why, if you have these two cases of Dirac and Majorana particle, neutrino electron scatterings in principle should be different? Why we don't see these differences in the case of neutrino electron scattering? The reason is because essentially, as we already said, neutrinos are left-handed. So since neutrinos essentially are born as left-handed particles, then you should add an extra term that tells you that the particles are left-handed. So if you put this term in this amplitude or in this amplitude, you should include in both amplitudes, because you know that the neutrinos are left-handed. Then it happens that both amplitudes became identical. So there is no way to distinguish between Dirac and Majorana neutrinos in neutrino electron scattering in the case you have neutrinos that are completely left-handed. The problem is that neutrinos are almost completely left-handed. So consider, for instance, the case of the decay of pseudoscalar meson, like the pion, which is the source of most of the atmospheric neutrinos. But so consider, for instance, the decay of a pion to a muon and a neutrino of the muon, and want to compute what should be the polarization of these neutrinos. So you can compute what is this polarization, and it is given in terms of the energies of the neutrino and the moments. And then once you plug in the numbers of this for the polarizations, you realize that the difference between this polarization and -1, which will be telling you that the neutrinos are completely left-handed, is 1 part in a million, 1 part in a billion, 1 part in a trillion. So essentially they are left-handed particles. So the approximation, but not the approximation, but the idea to add this extra FARC because neutrinos are left-handed to these two amplitudes is reasonable, and then that's the reason why usually you don't have, that's the reason why you don't have any difference with the neutrino electron scattering if they are Dirac or Majorana particles. But in any case, you can do the computation, and you can imagine, okay, so let's for the moment forget about neutrinos are left-handed particles, and then let's compute what is the dispersion of the neutrino with the electron, including the neutrino polarization, so this vector. So you don't know, for instance, what is the polarization of neutrino, where this quadrivector is essentially given, and then you have to choose some system of reference. In any way, you can compute what is the differential cross-section, including the polarization, and then for the case of the Dirac case is this expression, and in the case of the Majorana is this expression. So clearly they are different, at least from the analytical point of view. And then you can see that the cross-section depends, you can ignore the mass of the neutrino, but we have included the mass of the neutrino in this case. So the cross-section depends, of course, on what is the polarization of the neutrino. So if you take this cross-section for the case of the Dirac, consider the case where the mass of the neutrino is 0, and see if the mass of the neutrino is 0, and put here that the polarization of the neutrino is -1, so this value is 0, then this cross-section is exactly the same as this cross-section as you will expect. Okay, so in this case, you recover the things you were expecting. But then you continue thinking, what are the difference? Because although the difference are in terms of the mass of the neutrino and the value of the polarization of the neutrino, you can compute what is the difference of the Dirac and the Majorana neutrino, normalized by Dirac or Majorana. It doesn't matter, you can put here Majorana or Dirac, and then plot this function as a function of the energy of the neutrino. So essentially, here you can see what is the difference, and for typical energies of the neutrino, putting this value, so almost completely left-handed particles, so the polarization of the neutrino is almost -1, but the difference is in 10 to the -9, so it's almost completely left-handed with a mass of 1 electron volt. If you compute what is this difference as a function of the energy of the neutrino, you can see that for typical neutrino energies that we are used to measure, the difference is completely negligible. But if you consider a scenario unrealistic in this moment, and maybe for practical reasons unreasonable, for energies of the order of some electron volts, the difference can be quite big. So it is just a matter of principle. They are different. For very low energies, probably, so this is a question that I have in my mind. Relic neutrinos, the one that come from nucleosynthesis, now are typical energies are below these values. So in principle, there should be at those extremely low values of the momentum of the energy of the neutrinos, difference between Dirac and Majorana. I don't know if there is any observable for that, But in case it is, there should be some difference in the cosmic microwave neutrinos for those energies. But this is speculative, right? Yes.
Question now, so apologies. So this is for mass, the neutrino mass of 1 eV.
Yes.
And so then the energy is also 1 eV to get order 1 difference. Right?
Correct.
Right. But if neutrino mass is milli-electron volts, and similarly the energy would have to be that volts.
Correct. Exactly. Yeah. This is yes. Yeah. Okay. Anyway, still, as you can see, cross-section is a function of the polarization of the neutrino, so let's continue playing. So imagine that you can compute what is the total cross-section, and the total cross-section will be just the integration of the differential cross-section times some spectrum of neutrinos. So, and in order to make it easy, imagine you have some detector like Borexino, where you know what are the recall window and what is the spectrum for that they are looking, and then compute what is this cross section as a function of the polarization of the neutrino. Of course, we still have to think how we can get these values of the polarization of the neutrino, but just as a matter of exercise, let's do it. So what you recover is what you already knew. So when the neutrinos are completely left-handed, then there is the cross-section for the Majorana and Dirac case are equivalent. So you have this point where there is the equivalence between a left-handed massless Majorana neutrino and a left-handed massless Dirac neutrino. But then imagine that you can change what is the position of the neutrino, and then you change from -1 to 1. So you change the neutrino from left-handed to right-handed, and then in the case of the Majorana case, you go from this to this, and then you will have the equivalence of a right-handed Majorana neutrino versus a right-handed Dirac antineutrino, since you can compute what is the cross-section of a right-handed Dirac antineutrino, and they are equivalent. But in the case of the Dirac case, what you have is that you change from -1 to 1, so you go from a left-handed Dirac neutrino to a right-handed Dirac neutrino. The cross-section is 0 because it is essentially a sterile neutrino. Now, this is just an academic or a student exercise, but the question is, can you find a mechanism in astrophysics that can change what is the polarization of the neutrino? And the answer is yes. Actually, the nature gives us a possible way of changing this polarization of the neutrino. And essentially what you need is that the particle has a magnetic moment, and you need an external magnetic field. So essentially it's just a Stern-Gerlach experiment. So the neutrino interacts, its spin interacts with the magnetic field of the environment, and then it is going to precess so that the polarization can change. How much can the polarization change? Well, it depends of the medium or the magnetic field. So you can have an estimation of how much the neutrino has to travel in order to have a change in the polarization, an appreciable change on the polarization. So for instance, you can imagine the case of a random distribution of electromagnetic fields. In that case, the neutrinolicity, or the polarization of the neutrino, will change as given by some exponential of some parameter, and this parameter is given as a function of the typical temperature of the medium, where the random electromagnetic fields are, and the magnetic moment of the neutrino. So you can compute what are the distance that this particle, the neutrino, should travel in order to have a complete depolarization of the neutrino. So in the case of the sun, you can have a complete change of the neutrino as long as the magnetic moment should be of the order of 10 to the minus 11 Bohr magnetons. And in the case of active galactic nuclei, you can go a complete transformation of a complete depolarization of the neutrinos for these distances and so on. So in principle, there are places in the universe, astrophysical environments where wild magnetic fields exist, where the precession of the neutrino will appear, and then, in principle, the polarization of the neutrino can be different from -1. Let's take, for instance, the case of the sun. In order to see how much the polarization of the neutrino changed inside the sun, you need to know what is the magnetic field in the sun. So you need a model for the magnetic field. So you can go to the sun, imagine that it is a spherical cone, so spherical approximation. You solve the magnetostatic equations, and then you will have a family of solutions for the magnetic fields, and then you can construct the solution for the magnetic field inside the sun as a superposition of these functions, and then you impose some boundary conditions, and the boundary conditions that you impose is that magnetic field at the center of the sun should be 0, and magnetic field at the surface of the sun should be 0. So you impose these two boundary conditions, and then you can have what are the solution of the magnetic field inside the suns. So this you will have profiles that the maximum value of the profile will be given by the value of the magnetic field in the convective zone. So there are limits for what is this value, and then you can have the profile. Once you have the profile of the magnetic field, then you have the equation for the change in the polarization, which is this one, and then what you start assuming that you start with a neutrino, completely left-handed neutrino. As long as it travels along the sun, it is going to change. So at the end, the sun, at the end of the surface of the sun, the neutrino will emerge with a polarization different to -1. So in principle, the neutrino can have a different polarization from a left-handed particle. Of course, it depends of what is the profile of the magnetic field and what is the moment, the magnetic moment of the neutrino. So in this case, we can this plot is done for assuming that the magnetic moment of the neutrino is 10 to the -11. But in principle, you can play the game of what is the change in the polarization for different values of the magnetic magnetic moment of the neutrino. And then, so the picture you can have is that the neutrino initially is born as a left-handed particle, travels along the sun, changes its polarization. So at the end of the surface of the sun, the neutrino emerges with a different polarization. Then, of course, you have neutrino oscillations. The neutrino travels between the sun and the earth, and then you have your detectors. So you can, if you want to estimate what is the number of neutrinos that you will have in the earth, in the detection, essentially you need what is the flux, what is the cross-section that you are going to use to detect your neutrino, and you have the propagation, so you have the probability. This is the standard one, when you are neglecting the magnetic moment of the neutrino. But in the case that you introduce a magnetic moment of the neutrino, you should recompute what is the number of events. And the number of events, usually, what we are thinking is that it is only to change what is the probability. Because the probability can, after you introduce the magnetic moment, will depend on what is this value of the magnetic moment. As well, the cross-section change if you introduce a magnetic moment, because if the neutrino has an effective magnetic moment, then the neutrino can interact with the photon through this magnetic moment, and then you should include in this cross-section not only the electroweak cross-section, but the interaction of the neutrino with the photons due to this magnetic moment. But this is something that people have done in order to obtain limits for the magnetic moment. But what we are saying is that in addition to the magnetic moment that you have to introduce, since the cross-section depends on the polarization of the neutrino, this cross-section that you are going to plug here in your respective number of events should include what is the polarization of the neutrino. If you consider that the neutrino has a magnetic moment. So in such a way that the number of events depend on the value of the magnetic moment and what is the polarization of the neutrino, which as well, the polarization of the neutrino depends on the value of the magnetic moment. So this is a nonlinear problem. So you should solve this one for each case of the value of the S parallel. So in order to make a constraint on the magnetic moment using solar neutrino, you should consider the cross section that depends on the polarization of the neutrino, not only the correction that you have for the magnetic moment. This is something that we have to do, but for the moment we haven't done. We can just make some estimation about what will be the effect. So for instance, what we know is that Borexino had some relative, so it has some error bars, right? So in particular, Borexino has been able to measure this line of the beryllium, which is a Dirac delta for the spectrum. So that makes our integrals easy. So it is from imagine that this error, this relative error, arises entirely from a possible difference between a Majorana and a Dirac nature of the neutrino. So it is, in the case of a beryllium line, it is more or less straightforward to go from the number of events to our integrated cross sections by assuming that the magnetic moment for the Dirac and the Dirac and Majorana cases are equal, which is not the case. But just we want to do an estimation of what will be the effect of introducing the change on the polarization on the determination of the number of events. And then essentially what we are saying is this difference, this relative error, should be as big as the difference between the Dirac and Majorana cross-section integration, which we know it's a function of the polarization of the neutrino. So you can do the game. So you can compute what is this difference between Dirac and Majorana as a function of the polarization of the neutrino. So you assume that Borexino different in the case of the beryllium line, the relative error is telling you that the difference, if the possible difference should be smaller than this, so the maximum change that you can have on the polarization of the neutrino should be less than minus 0.4, and then by solving this value for the polarization of the neutrino as a function of the magnetic moment, then you realize that the magnetic moment should be smaller than this value in order that the polarization doesn't change as much as this value. And then you have an upper bound on the neutrino magnetic moment. Of course, this is hand waving. The real analysis should be done where we have to include the cross section with this new extra term that arises from the change on the polarization, the probability that depends on the magnetic moment, and then compute the number of events and integrate everything. So the process should be done, and we believe that the limit that can be obtained will be stronger. Well, what about other sources where you can change the polarization of the neutrino? Supernova are one of these sources. So actually, as we have already mentioned it yesterday, the people who are doing simulation of core collapse supernova are improving year by year, and then actually now they are able to say what are the magnetic field that is producing during the collapse. And actually, the relevant point here is that you can have huge magnetic fields in supernova explosions. So you can see, for instance, this is the profile of the magnetic field as a function of the distance from the center of the star in Gauss. So you can have, I deleted here the 17, but you can have 10 to the 17 Gauss for distance of the order of kilometers. So imagine that you have some profile like this one from a supernova. So imagine that you have a supernova, the supernova explodes, it produces a lot of neutrinos, but in addition to the neutrinos, you will have the profile of the magnetic field, so the neutrino will precess within this strong magnetic field. Of course, this precession depends on the magnetic moment. So assume that the magnetic moment of the neutrino is the one that the standard model predicts, 10 to the minus 19 Bohr magnetons. And plug this, what is the change of the polarization of this neutrino with this extremely low magnetic moment in magnetic fields of 10 to the 15 Gauss in 100 kilometers traveling. What you finish is that the final polarization of the neutrino will be changed, even in that case. And the change will be as from -1 to -0.35 or something like that. And then you can compute, again, what it will be the spectrum of neutrinos as a function of the recoil energy, and you have clearly difference between the Dirac and the Mariana cases. So what I am trying to say here is that possible, I don't know, the devil is in the details, but from these very easy estimations, changes on the polarization of the neutrino can be big, and these changes in the polarization change cross sections, and these cross sections, this is neutrino electron scattering, so an experiment like Borexino that detects some neutrino electron scattering, assuming that this polarization have changed, may have some differences between Dirac and Majorana. Not percent difference, but something possible. I don't know. In conclusions, well, still we don't know many of the properties of the neutrino. This is an open, interesting, exciting questions that we have about what is the neutrino and what are the properties of the neutrino. I am very happy that I choose to study neutrinos when I started graduate studies. So thank you very much.
We have time for many questions.
Oh.
Yes, thank you for the nice summary. Thank you for the nice summary. Going back to your last slide, and you said the standard predation of 10 to the minus 19. Again, it's assuming a 1 eV. That the mass is 1 eV.
Yes.
And otherwise you get suppressions accordingly, right, to the suppression in the mass. My question is, because of this, and if the ordering of the masses is indeed normal, how there might be hints might be the case, you would have a difference between electron flavor and the other two flavors.
Yes.
And now, while electron scattering, of course, is disadvantageous for the mu1 and the tau flavor in terms of cross section, that is by a known amount. And so, can one study the flavor composition of that structure more in detail and get some information about this?
Well, yeah, I don't know. Probably yes. My answer should be, I guess, yes.
More questions?
Thank you very much. It was very interesting, and I have a series of questions that you can help me to understand better.
Yes, yes.
So starting with, so if neutrinos are Majorana particles,
Yes.
then the static magnetic moment has to be 0, right?
Yes, so in principle you have, in the case of the Dirac-Majorana, in Dirac magnetic moment, it is a diagonal Well, actually, it shouldn't be diagonal. It can be any kind of, in the matrix, it can have any places.
Right.
In the case of the Majorana, it should be non-diagonal
Right.
magnetic moment.
Okay.
And the structure should be given by the flavor composition. So it is, this magnetic moment that I am putting here is a combination of the.
That's right. Okay, so then the standard model, 10 to the minus 19 Bohr magneton, this magnetic moment. If neutrinos are Majorana particles, this standard model magnetic moment term still exists or no? I don't.
Actually, if neutrinos are Majorana, the expectation of the neutrino magnetic moment should be bigger than 10 to the minus 19.
So then this diagram that you draw.
Yes. So you add
bigger.
all these diagrams that you have to introduce, assuming that the neutrino is antineutrino and so on and so on. But you have to add some extra new physics on the calculation of the magnetic moment. I don't know exactly the details.
Yeah, I don't know it either.
But in principle, yes, you can have. Actually, in my bottom of my hair, of my brain, it says that I remember that conclusion is that if neutrinos are Majorana, magnetic moment should be bigger than the Dirac case.
Right, but that diagram, when you draw it, has to have the flavor transition, right? Or it has the mixing, right? In order,
Exactly.
otherwise, it should go to zero, right? In principle, right? Otherwise, it'd be sort of equivalent to the static case. Right? Maybe
Yes.
not, yeah. And then, if neutrinos are Dirac particles now, then if you have a magnetic moment and then the polarization changes from the magnetic field, what happens again to the cross section? I think maybe
Yes.
you just show that, then I think that answers all my questions.
Oh. So this is the Majorana case, and this is the Dirac case.
So the polarization is there. Yes?
So yeah, the polarization is this guy, and actually, so to make it easier, consider the case where the mass of the neutrino is 0, and then let's try to you just do the algebra, and essentially the case of Dirac as a function of the polarization of the neutrino can be written as the Majorana plus 1 minus S parallel extra terms that doesn't depend on the mass of the neutrino. So essentially, there is a factor 1 minus S parallel difference, and that's the reason why you have this as long as S parallel changes.
Right. So if they rotate the polarization because of magnetic field and magnetic moment, then it's not the case that it becomes a right-handed sterile neutrino.
Yes, this is the case.
It
So
is.
the Dirac goes from the value that it has to sigma equal to 0, which is sterile neutrino.
I see. Okay, so it is.
Dirac, so you have from the Dirac goes from the Dirac neutrino to a sterile. The Majorana goes from equivalent to the Dirac
Right.
to antineutrino.
I see. Yeah, no, that's good. Thank you.
So here. So how was the equation derived? The equation you showed us that.
Change the
Flick the-
polarization.
yes.
Yes, is this one.
No, yeah.
So essentially, it's proportional to the magnetic moment and the strength of the perpendicular value of the
And
external
the previous
magnetic
one,
field.
the previous slide? Or that one?
From this, you can arrive to that.
Uh-huh. What are the,
Other things, so this is, I don't remember, but it has to do with you can change you can have changes in the polarizations, and you change the space, for instance. So neutrino can change its polarizations, for instance, nearby the black hole, for instance,
okay.
because there are metric coefficients here, and honestly, I don't remember very well, but the important fact is that you need magnetic moment different from 0.
And if you had a nanopole moment, would that, because that's affected also by the magnetic field? would that-
This is unaffected, so it doesn't matter if
Ah,
it is
okay.
an
That
apole.
comes from somewhere?
Exactly,
Okay, and you don't know exactly?
exactly. We don't care if it is a combination of different non-diagonal.
Okay, okay. No, that's my question.
More questions? So we thank again for
Thank you.
then sorry. The next speaker of this session is Andrea Pokar, who will talk about solar neutrinos and Borexina.
Is it on? Yes. Okay. Dragging it as a tail. All right, this should work. So I'll continue where I left it off yesterday, and you might see that I've added a little and beyond note on the talk, because I'll mention something about a program of looking for neutrinos from the sun with a very large liquid argon experiment, which might have unique sensitivity to some of the neutrino fluxes. Before I proceed, this is actually an important day for me. My mom passed away 2 years ago today, and there's a funny coincidence. My parents came to the Americas the first time in '78, and they came to Mexico. And so I was told that this was one of her favorite trips that she took, and so I'd like to remember her today, which is a special day for me. Moving on, this is the last slide I left yesterday with the phase 2 Borexino results with a precision measurement of the beryllium-7 flux and improved PP and PEP neutrino flux measurements and an improved boron-8 measurement. And as promised, yesterday we started talking about metallicity. And metallicity requires further effort. Metallicity in the sun and the amount of heavier than helium elements in the sun is an open question. I refer you to these papers, but basically there's predictions with models with where the metallicity is higher and lower about the various fluxes, and these fluxes change somewhat.
The beryllium-7, for example, changes by something like 12%, which is a measurable, possibly a measurable number. But by and large, the largest effect is going to be had with the CNO neutrinos. And so if you actually dissect the neutrino fluxes, PP, boron, beryllium-7, boron-8, and the CNO components, you see how the CNO actually have a large difference. The beryllium-7 has something of order 10%. So what can we say with what we've done so far? So beryllium-7 changes somewhat. And so if you plot the fraction of beryllium-7 and a fraction of boron-8 on a two-dimensional plot, this is something that we've presented already starting at TAUP with the papers from the summer. We see that unfortunately our data doesn't really disentangle between the high metallicity in red and low metallicity in blue centroids, but also there is theoretical uncertainties depicted by these ellipses that really, with these neutrinos, there's still a high amount of uncertainty. Our data are definitely compatible with both from the purely statistical point of view. You can see the same data in a pictorially maybe more appealing way, but the statistics behind it is the same. On our survival probability plot of survival against energy, we have our 4 neutrinos from the PP chain, the boron-8 down to the PP. The sort of survival expectation is in pink, and the high metallicity evaluations fall a little better on that curve than the low metallicity one. And so from a purely sort of optical point of view, this is a better plot than this plot, but you can see how the distances here are just a fraction more than a sigma, and so you can't really tell much from what we have done so far. Obviously, if one can shrink these errors further, one can start seeing more possibly, but Borexene itself will not be able to really shrink these dramatically in any we've run now for a decade. And so CNO is certainly a very appealing thing to go and look for. And as I said yesterday, the CNO neutrino flux on the electron recoil plot, that is our usual standard plot, falls down here. It's a beta spectrum that has a shape down here. And its height with the height of the PEP neutrinos and backgrounds that fall into this energy bin add up to this valley between the beryllium-7, and this is a type of course, and the carbon-11 background. And so measuring the height of this valley could produce a value for the CNO. And in fact is what we have done so far. We've used this fit to constrain the flux of the CNO. And here I try to exemplify what the issue is, though. This is the CNO from our simulated plots, PDFs. This is the PEP. And in a fit, one can also use the fact that the PP and the PP are constrained by known physics, so you can make that assumption, and use the fact that theoretically the PP neutrinos are known to 1%. So you can further constrain things. So you can basically fix the PP in the fit, but you're still left with this background, this bismuth 210, which is part of the radon chain. And you can see two things. One is, so far, it's actually higher than the CNO predicted rate. Secondly, it has a very similar shape in the spectrum. So it's very difficult to disentangle these two spectra because they're certainly not fully independent in the fit. So CNO. CNO has the issue of bismuth 210 background in the scintillator. That's our issue. Bismuth 210 can be purified in principle, and we've done factors of a few in our 10 years of operation. So certainly there is a plan possibly to purify further the scintillator. This is is still debated within the collaboration as to whether this is something that we can actually manage and do with the other things that we want to do. But there was an interesting proposal in 2011 from these authors that it's enough to know the bismuth-210 well enough and know that it's stable over the time of the data taking to constrain it in the fit. If you have a handle of measuring the bismuth-210 abundance some other way than just a fit parameter in the fit, then you can plug it as a constraint in the fit, and then possibly you can extract the CNO. But the key problem has been, is this concentration constant over time? And the answer is actually, it's been no. And so we couldn't really make that assumption. But the technique would go, if everything is homogeneous and uniform, then we know that the lead-210 decays with a half-life of about 2 decades. And the decay chain goes to bismuth-210 and then to polonium-210. And so if we can map the decay of polonium-210, which on the other hand is a fraction of a year, well enough, then we can do a fit with an exponential with a polonium half-life and a constant term. And if we can extrapolate the constant term, that is the amount of bismuth-210 that we have. So if we can measure this constant well enough, then we can constrain the fit. It's, in principle, very simple. In practice, it's not that easy. It's not that easy because we have a detector that is liquid, and liquids experience convective movement of their mass. And so here I show the background, so it's a slice of the detector, of the sphere, that shows the events in the energy range of bismuth-210, of that valley, of some slice of energy. And it shows how we definitely see the vessel. There's more background at the vessel. We certainly see the 2 poles, which is where plumbing comes into the vessel, and plumbing is made of plastic, but it's massive. There's quite a bit of it, and it's not as clean as the liquid. But then we see residuals. And snapshots at different times show these things move around. They're not always statically like this. If it were, and we could prove that the scintillator is static like this, then you could maybe cut out a fiducial up here. You give up half the detector, but you can do maybe physics. But we have not been able to do this. And the problem with convection is that a convective in a sphere onsets like cells like this, and the flow along the surfaces brushes against the vessel, picks up the residual amounts of background that has deposited on the plastics, and then stirs it back into the volume. And convections are seasonal because you need a thermal, and you need the flow to become colder at the top at some point in time and then start sinking and then moving fluid like that. So the key to not having convection is to stabilize the temperature from warm to cold. The cold below is driven by the fact that the detector sits on the rock of the cavern, and that rock has a temperature that is virtually constant. But the rest of the detector is exposed to the Hall air, and that air changes temperature with the season outside. So this is actually the polonium decay. When it's abundant, you don't see the subtle effects. You see it decay, and the red and blue are the top and the bottom of the detector. So the half top is red and the bottom half is blue. And you see that when the activities become low, where we like them to be, things start jumping around, and they actually cross. So the activity at the bottom becomes lower than that at the top at certain times, and they start crossing. And that's because the fluid is just mixing. And this is profiles of the temperatures in Hall C. And so we have never been able to say we have a stable detector. And here is the log plot of this one, and you can see the nice exponential behavior up to the point when things start mixing up. So what we did is we put a blanket on the detector. So this is a detector before, exposed to the air, and there's a huge surface that contacts the air. So the heat exchange is actually quite substantial. And the heat exchange from changes in temperature in the air through the stainless steel, which has its own abundant heat capacity, through the water tank, through the buffer scintillator, and so on, is months. So you have to wait for months to see that the detector is stabilizing. Waiting a week doesn't help. You will not know that the detector is stable. In fact, it's not stable on the order of months. So we started insulating the detector from below up to the top. It took some time. And these are the probes in the outer parts of the fluids before the insulation. The insulation starts about here. And you see how these temperatures really go up and down. And at some point here they start stabilizing. Now the insulation started here, but it took some time. So the bottom part of the detector starts cooling down to the temperature of the rock. The middle part starts stabilizing, and the top waited until the insulation got completed. And this is after the insulation was actually completed, and you see now over the course of about a good fraction of a year how stable the temperatures have been. This is kind of obvious in hindsight. I mean, you just thermally insulate things and things become stable. And then at the top of the detector, we actually have an active heating loop that provides some heating power at the top in order to maintain this differential. We like the gradient. We like it to be hot on top, cold below, so that convections are inhibited inherently. And this is another way of seeing those temperatures. So the fluids in the detector, the 3 volumes of scintillator or solvent, are connected to head tanks that have a level, they have an overflow. So when the detector gets hot, it expands. It's a lot of mass, so you have to empty it out in overflows. But this is an excellent way of measuring temperature. You measure a level to a millimeter or 2. You have hundreds of tons of mass. This is very sensitive way of measuring temperature. It's very expensive too and very inconvenient, but it works well. And so since the insulation was complete, and once we actually turned on the active control at the top that heats up the top, you see how the refills of scintillator, so this is the height of the fluid as a function of time, and you see how the fluid cools down and shrinks, and you have to refill it after a warm period of time. And the refills got rarer, we had to refill less and less. And then at some point, with the help of the summer that is warmer, we started seeing a very stable temperature of the fluid. Now this is 1/100th of a degree C, just because the mass is very large. This is another way of seeing the data. This is, again, the polonium energy window over time. And we've segmented the detector in cubes. And the cubes are like, a first floor of cubes, a second floor of cubes. So as you go up in number of cubes, you go from south to north. But it's not obvious to know exactly where you are unless you have the map of where the cubes are. But by and large, low numbers is the bottom of the detector, and high numbers is the top of the detector. And you can see how the clean volume was moving from the top to the bottom, to the top, to the bottom, until the insulation was added. So the cleanest part of the detector was moving. And some people have said, well, why don't you do physics cutting out that? Yes, sure, you could do it, but how do you evaluate the systematic effects of that? I think it's impossible. How can you make a claim of measuring something for the first time by doing that? I think it's, you get on sketchy areas of how you claim a finding, if any. But then we insulated the detector, and you see how the detector is much, much stabler. Now I want you to focus on the last slice of time. Things got stable, and you see how the blue now is starting to protrude down to the bottom. This is a sign that polonium seems to actually be decaying again as expected. And so the hope is, will we have enough time here to measure things? And this is a question that I cannot really answer completely. I cannot answer completely because there's a SOX program coming. And as I mentioned, The SOX source is planned to be delivered at Gran Sasso in the spring, in April of 2018. And for the SOX program to be successful, we need to calibrate the detector in order to calibrate the detector at its edges and measure the neutrons and the gamma rays very close to the vessel in order to use the entire 300 tons of scintillator. But if we calibrate, this has to happen early in 2018, and so this gives us maybe another month or two of data, which is kind of unfortunate. Because we're really kind of right there. Now, if you did what I suggested and Googled Gran Sasso SOX, you probably will have hit sites, blogs of protesters. So there is actually protests going on at Gran Sasso from the local population that has found out that the actual SOX source is a very, very hot source. It's fully sealed, and I'll say something about it. But anyway, at this point, operations at the lab are at a standstill. And so while this is unfortunate for a number of reasons, not just for SOX, but even for the whole environment and climate at the lab, these are not good events for science, I will say. They could yield one positive outcome, and that is that we'll just run for longer. So stay tuned and we'll see what happens. Now, on the grander scheme of things, we might think of calibrating, and I might say something about that. Actually, I will say something about that. But the goal for a calibration, for a purification campaign, would be to reduce the bismuth 210. And it was found, actually, that standard distillation of water even doesn't really get rid of polonium and possibly of lead. And there's actually interesting findings that some organisms actually use dimethyl polonium to live. And so making a volatile compound that if you distill just goes into your purified product. And so the purification schemes would require and involve going from a system where we take the water from the purification plant at the lab, which is a rather standard purification plant, a very good one, but rather standard, and then recycle the water and re-distill it and in a closed loop so that you don't reintroduce impurities. And then there's actually an idea to use the water from the CTF tank that has been there for years, so polonium has certainly decayed away overall, and start from that one to use for the purification in the detector. The plants are essentially ready. They need a little bit of commissioning and they need a cleaning step. But plans exactly of if and when to use them are up in the air. So going on to SOX. SOX is a program to investigate the anomalies at low energy and possibly search for sterile neutrinos with a cerium-144 antineutrino source. The goal is to probe oscillations at the meter scale or at the delta m square of roughly 1 eV squared. This is some of a contentious issue, and it is very possible that the recent Diabay measurements of the antineutrino flux from reactors have weakened the case for the physics behind it. Nonetheless, I think SOX is a very clean way of measuring this. We have a plan. It's different from all other efforts at reactors, and so I think it's a valid experiment. It's a good experiment to make. Even if we don't see anything, this is details of the source, and really the antineutrinos we are interested in are not the ones from the cerium-144, which is what determines the lifetime of the source that we have, but it's those from praseodymium-144, which are higher energy. And we need that higher energy to overcome the threshold, 1.8 MeV, to see antineutrinos in the detector. As a coincidence, hence with essentially no background. And so the plan is to put the source under the detector, keep it there for a year or a year and a half, about a couple of taus, and measure antineutrino events throughout the scintillator. The gallium experiment had done something similar with a chromium-51 source. This is a neutrino apparatus. And they had placed it next to Galax to calibrate the detector, and this is sort of how big such a beast is. The cerium source is similar in size, and it's encapsulated into a tungsten container that acts as a shield and as a sealant. And this is the tunnel below the detector. So now the tunnel has rails, so it's going to be put on a cart and just pushed in and left there for a while. This is how the source will get to Italy. It's produced at Mayak, which is a reactor in Russia. The fact that it's produced at Mayak and not other reactors has been an extra problem with PR, because Mayak in the past has had accidents. And so people looking it up will say, oh, that's where Russia had accidents. And so obviously all this does not help. But basically the cerium-144 is a product of fission, so it's separated from nuclear fuel, so it's a pretty delicate operation. It's separated, it's put together into 150 kilocurie of source, which is quite hot. It produces a lot of heat. It's put in a canister for transportation. It gets on a boat. It gets to France. It will get to Saclay and then to Italy. So France basically imports it into the EU, and then it gets to Italy. Overall transport time planned is about 3 weeks. You lose about 5% of the activity, so this is manageable. But of course, you can't really extend much beyond this. If you start having delays at any point, which is I'm not saying it's likely. I'm saying it's possible though, and everything has to really run smoothly. And so you don't want protesters blocking the road, But these are real things. They're not things you can neglect. You really have to face them. But going back to physics, there's two ways of doing physics with it. One is counting the rate. So you measure the total number of events you see in the scintillator. You compare it to the expected amount. The expected amount is based on knowing the activity of the source to 1%. And that is done by measuring basically the heat output of the shield. And then comparing it to expectation. So this is an absolute type of measurement. It's hard because it's 1%, and it has to be so in order to address the anomalies, interestingly. The other way that really addresses the oscillatory sort of aspect of oscillations is that you can measure the rate as a function of distance in the detector. This would be nice if you see a hint of an oscillation. Obviously, that would be, you don't need to normalize the activity of the source, in principle, to claim new physics. However, it's hard because you bin up the events, and so you have fewer events per bin, and so the error for each bin is higher, and it's a harder thing. But of course, both will be done. And if you do these, you see the sensitivities of the two approaches. The rate-only approach is in red. The shape-only approach is in blue. And if you combine the information from the two, you get the black line for sensitivity of exclusion of any oscillations. And this blob roughly summarizes where the anomalies stand. I think probably various authors might have their own flavor of this island, but roughly speaking, this is where it is. And this is where most of the proposed or running experiments at reactors are trying to probe. So this is going to be an interesting complementary effort. This is another plot from a previous paper that hasn't really changed much over time. Borg-Sino has done many other things, and in particular with antineutrinos, we've seen antineutrinos from radioactivity in the rock of the Earth. These were first reported as a hint in 2005 by Camblin, then Borg-Sino made a slightly better measurement in 2010, and then it was we both sort of had a horse race on this. from, we know, well, we have some estimates about the radioactivity of the Earth. We certainly have samples of the crust where we can drill a hole, take material out, and count the uranium, thorium, and potassium, and measure its concentration, and then translate that into a power. Neutrinos are detected via inverse beta decay, producing a positron and a neutron that have a characteristic coincidence. And this is Borexino's latest data. Camlin actually has a recent paper that I haven't included here, which increases even further. But this was a paper in 2015 where we saw a best fit of 24 events from the Earth. And as you can see here, the antineutrinos from the Earth are the low energy part. And one is the uranium chain, and the other one is the thorium chain. And then the orange blob here are neutrinos from reactors. Now, Italy doesn't have many of them at all. None of them is actually active. There were 4 which have never, a couple of them have run, and a couple were almost about to run when a vote decided to abandon them altogether. So these are actually antineutrino events from reactors mostly in France. So we actually saw baseline, events from about 1,000 kilometers away. And the detector is clean enough, and the coincidence technique makes it background free, that we could actually count, order of 10 events from France, which is remarkable in and of itself. Of course, statistics are low. But as you can see here, background is included in the plot, but it's like less than one event. So basically, this technique has no background for us because our singles rate is so low that you can just neglect it. And you can start playing around with some Earth science, and as you gain statistics and you combine experiments that live in different places where the crust has a contribution. So the 1/r argument tells you that most of what you see is from the crust around you, just because the flux is much higher. But if you measure for long enough, you can start making some assumptions about the mantle. And that's interesting because models of the evolution of the Earth and how elements have mixed between various strata of the Earth find this quite interesting. And then you can start trying to separate the composition of uranium and thorium in the Earth. And for that, you need enough statistics. So our data is not yet enough to really distinguish, but you can start comparing against models. And so we have best fits, essentially, for this. Then we did other exotic things. We looked for electron decay. Now, of course, electron decay would be a disaster for most field theories. So, the collapse of the U1 symmetry and whatever. And so, but since we know how to do it, we have the data, you do it. And basically, you look for a gamma ray of a given energy. Now, there's other modes you can study, which are blind to us, maybe, but you can study certain things. And we set a limit. And this was done basically with the data that we use for the PP, because you look for a gamma ray in here. Magnetic moment, we just heard a very good introduction to all this, so this slide is redundant, and why it's interesting to look for it. So this would be the standard process of a Dirac neutrino. But you can have transition moments in more exotic scenarios. And Borexino has actually set some recent limits on this. Let me go relatively quickly. So we explore the variation of the neutrino electron recoil spectrum at low energy. In principle, one could do it with the PP flux and the beryllium-7 flux. Really, the beryllium, the PP flux to us is blind because the deformation is under the C14. So we have absolutely no sensitivity to it in a liquid scintillator target. However, with the beryllium-7, we can start trying to see this deviation. The red line is for an exemplary case of a 510 to minus 11 mu b. And then, of course, you study it. You study the profile of the likelihood, and then you use this in the absence of a clear deformation to set a limit, and that's what we have done. And so basically, we set the limit at 2.8 10 to the minus 11. This is on the archive, so it's totally public. It's not new. We presented it about 2 months ago for the first time. This is sort of a comparison with the leading terrestrial experiments. And then we have also set limits on the flavored parts, which are similar, not quite as stringent, but similar. But these are possibly even more interesting because these could be closer to new physics. Because this is the Dirac thing. And we know that the standard one is so far below that there's no expectation to actually see it. Of course, if you see something, it's very new. But on the other hand, the constraints to date on these are less stringent, are less defined, and they're actually a little above the constraints for the Dirac case. And so this is cutting into interesting land to some extent, although obviously we're not really expecting to see an effect. But our analysis now has become much more evolved. Looking ahead, I think we're pretty much done with this. This is 10 years of data. Well, it's 5 years of data, of the best data we have, but we ourselves, I don't think we can really get much beyond this. But it's a proof of principle that a larger, cleaner experiment could in principle do better. The other thing that you touched on earlier is, well, if a star explodes around us, we have a number of ways to detect neutrinos from the sun. Elastic scattering actually is not our preferred channel. We clearly have a very good handle on anti-neutrinos, and which should be abundantly emitted by such events. Because the background essentially is zero, and the rate is actually quite high. So if we see a burst of tens of events in a very short time, that would be fantastic, of course. We think we can see the new P scattering. There's a little bit of a question mark here that has to do with the light output of proton recoils. There's a quenching effect, not as much as say for alphas. And we don't have a calibration for that very specifically. We have some data from source insertion that might have some of it in it. And so, but certainly if we see a burst of things, then we'll have to go back and really look at this data very attentively. And then there's inelastic scattering on C12 that then emits a very energetic photon that certainly we can see very well. A 15 MeV event for us is something that is so obvious that we should not be able to miss it. So anyway, let's hope this happens actually in the lifetime of, and of course this can definitely be done on top of SOX, because you're talking about a time window which is very modest. And then we did correlations with GRBs. We looked for neutrino events, bursts essentially, with known events in the sky. We didn't find anything. We set limits. I think we're far from interesting sensitivities on that, but I'm not an expert in the field. We had to look for coincidences with gravitational waves, and we did. This is sort of the time before and after known events, and we see a few candidates compatible with the rates that we have, so we didn't claim any signal. Again, I think we weren't, if we had seen signals of objects so far away, they would have depleted the entire energy of that event, and so it wouldn't add up. But I think we had to go and look. It was too good to be true. This is a Borgsino collaboration in institutions. This is us. This is the CTF structure where the PMTs for the CTF were mounted. Now it's a sculpture outside in the yard. Let me turn to the argon idea. I will not go into why searching for WIMPs is interesting, but you can do that with argon and look for recoils of argon, and this requires experiments which are super clean, super sensitive to low energy events. There's quite an industry around trying to do this with argon and xenon. As the xenon experiments currently lead the field. Argon uses some similar techniques. Currently there are technology proofs, both the Deep 36 and DarkSide 50 experiments don't have the leading sensitivities. Let me talk about the DarkSide experiment. This is DarkSide 50, the TPC before it went into the cryostat. We have plans of a 20-ton experiment instrumented as a dual-phase TPC with 20 tons of low radioactivity argon, and I'll say a little bit about this, but I don't want to really devote the talk to the details of this detector. We use ionization, scintillation and ionization from each event with the technique of the dual-phase TPC. So we have characteristic delayed, we call them S1 and S2 events that characterize events in our detector. Very importantly, electrons and nuclei recoiling in the argon produce different profiles of scintillation pulses. The recoils of nuclei are very fast. The electrons have this long-lived tail, and in argon this is dramatic. It's nanoseconds against microseconds. So you can do this separation exceedingly well. We've proven close to 10 to the 8 separation between these two classes of events. And so you can have a detector that has actually beta activity in it and not care about it for WIMPs. These are some pictures of DarkSide 50. This is the cryostat, this is the TPC, this is the water tank surrounding it with reflector acting as a muon veto. This is data at no field, and you can see the black line is the first run with atmospheric argon distilled out of the atmosphere that you buy from Linde or your favorite company. And you can see that there's an argon-39 spectrum. And while we can discriminate the argon-39 exceedingly well, at some point when you scale up to many tons, your trigger rate is just too high. Your detector is always on. And we look for these coincidences, and you start really not being able to do a very large experiment if the argon-39 is too high. And so we discovered that argon from underground wells in Colorado, in this case, are highly, highly suppressed in this isotope because this is produced in the upper atmosphere, cosmic rays in the upper atmosphere. And so the run with the underground argon is the blue line, or the red line. And you see how the gamma backgrounds from the cryostat and so on are the same, but what is gone is this prominent beta spectrum. And we measured a suppression of a factor of larger than 1,000. We also found that krypton-85, again, krypton-85, is actually leaked in a little bit into this sample. We think now this is from an air leak, not from a production mechanism underground. In principle, nuclear processes could occur underground that produce these, like fission. We know there's a little bit of it, and krypton could be a product of that. And certainly to some extent there is some. But it's interesting how we found the krypton-85. It was this deviation between the black and the blue that told us that there was a component with a higher endpoint. And we were able to extract that and then separate in the fit. We also saw the argon-37 peak in the early data. This is the argon-37 Davis has measured in the chlorine experiment, so this is kind of a nice thing. And it's a very low energy peak, and we saw it decay with the half-life of a month or so. This is not a concern. It's activated probably in the transport of the argon from Fermilab to Gran Sasso. Then we discriminate gamma rays that often multiple scatter around the detector, and we can see these multiple interactions in the detector. This is another way to discriminate the background. Neutrons, though, are the biggest concern for WIMPs, and so we surrounded the cryostat with a liquid scintillator detector, which is borated, so the neutrons always will capture in there and produce a characteristic pulse gamma, an alpha, or just an alpha, and so we measure these things. And if we see a signal in the veto, we veto any event in the TPC as not a WIMP. And this is data. These are all the residual argon-39 events on the underground argon. This is a much more abundant argon-39 in the atmospheric argon. And this is the discrimination parameter. So we build a discrimination parameter based on this pulse shape, on the timing of these pulses, and then we search for WIMPs up here, which are recoils of nuclei hit by WIMPs. And I want you to pay attention to the scale here. This is the atmospheric argon. There's a lot of events, and this is the underground argon for a larger exposure. And so for the underground argon, we were actually able to push this box a little lower. And we set a limit, which, as I said, is not the best in the field, in the cross-section of WIMP-nucleon interaction as a function of mass of the WIMP. All these curves go quickly up a low mass because your sensitivity becomes very low. The momentum transfer to a nucleus becomes very small, and it's below your threshold. And at high mass, you just follow the fact that if you need a certain amount of matter, if each particle is heavier, you have fewer of them proportionally. And so the density essentially of particles is this rise. Looking ahead though, we are planning to push liquid argon to really sample much below, especially at the hundreds to 1 TeV mass scales of WIMPs, where we believe the Xenon experiments, which are planning the LZ program and the Xenon 1-ton program and a third one in China, we think they have fundamental issues with radon-related events and possibly with neutrinos from the sun as backgrounds now. And so this past summer, we have formed what we call the Global Liquid Argon Collaboration, where everybody working on argon experiments for this kind of science has joined, all the collaborations. So it's the DEEP collaboration, the Dark Side collaboration, the Mini-Clean, and the RDM collaborations are now one. And we're having a 20-ton experiment as our next experiment, which we all will do at Gran Sasso. And then we have already an understanding to make a 10 times bigger experiment or so somewhere that can really start mapping this region here, which is the regions of atmospheric neutrinos that we know exist, and we've measured them extremely well, which would coherently scatter off nuclei in a process that we heard about yesterday. And so reaching this floor, as people call it, first of all, gives us an expectation. You ought to see a signal, and it's a well-quantified signal. Of course, you hope to see above the signal. But if you start not seeing it, you start questioning your sensitivity again of what you have done. And then, there's a parameter space that we know how to probe, and there's a very clean avenue to being able to doing so. So this is DarkSide 20K. It's big TPC. We're designing, and actually, we've just got funded by an INFN and NSF to do it. So this is happening. We're using silicon PMs instead of PMTs because these are very radio clean, and they're very beautifully single photon devices, and we'll read them out in tiles of 24. This is 25, but the final ones will be 24. And we hope to, with DarkSide 20K, to come down a big step in sensitivity, and then with another factor of 10 to go beyond this. And let me try to put it a little bit into context. So why heavy WIMPs? There's probably a lot of people who think, well, because SUSY has not been seen at the LHC, heavy WIMPs are unlikely, and this might be an argument. On the other hand, the LHC and its model-dependent statement, so this line is a fuzzy line, it's not a sharp line, has sampled, some scenarios of mass scales of WIMPs. And WIMPs might not be SUSY related. At this point, all bets are open, I think. And but even SUSY people say that there's actually quite a fair parameter space to be sampled for heavy WIMPs of order 1 TeV. This is our plan on gaining sensitivity. This is very easy to draw. It takes a lot of work to actually enact. Underground argon is a key component. We have done this for a dark side 50. We extract it from a CO2 stream in Colorado, where the argon is only 440 parts per million, and with a device called a vacuum pressure swing adsorption filter, which is, in fact, based on the same technology that we use for radon suppression at Princeton. So there's a recycling of knowledge and technology of a lot of people. We concentrated it, and then it was sent to Fermilab to purify, and then it was separated out and sent to Gran Sasso with only trace impurities in the end. And now we are expanding the plant to be able to extract 100 kilograms a day instead of in a year and a half. And so we're building what's called Urania, which is a full-blown industrial scale plant on the grounds of the company. Actually, we signed an agreement, and this is actually a parasitic activity in a way. So the discovery of this underground argon and the fact that the underground argon contained a fair amount of helium, which is quite easy to separate if you do it right, attracted business to actually extract that and commercially. And so we'll take the stream, part of the stream, extract the argon, and give it back for them to extract everything else they need to extract. So this has become actually a big operation. We are starting to write the tender for this. So in the next year or so, we should be in construction mode already. And then there's another crazy idea, but it's actually kind of interesting, and it's something that is actually funded at this point, and it's a really, really, really long distillation column, a low temperature, the size of the Tour Eiffel, in a mine in close to Cagliari. There's a lot of local interest in revamping a depressed area economically, so that was part of the game. And we will use this column to purify the argon coming from Urania, and possibly, if needed, to further isotopically separate the argon, another factor of 10 or so. You can actually isotopically separate elements via distillation, but this is a very long column. You have to do a lot of stages. So again, this is under construction, and this is me at CERN 2 weeks ago with some of these elements of the prototype column that are being shipped to Italy soon. So this is actually happening, and CERN has a role now in this because they do all the testing of these. They do the cryo testing, the leak checking, and everything. They have the people and the spaces. I mean, their spaces are so enormous that they can use, which is great that they help us out. This is the collaboration with the latest edition, I think, of the Canadian contingent, and neutrinos. So as promised, let me have a slide on what a 100 or multi-100 ton experiment can actually do for neutrino physics. Now, even depleted, and even underground argon with further depletion from ARIA, we will still have a residual argon-39 activity that will prevent us from doing PP. It's just, that's out. However, we can do beryllium-7, PEP, CNO exceedingly well. So if the backgrounds are what we're designing for in terms of radioactivity. Now, for neutrinos, we cannot use the discrimination anymore. These are electron recoil events. So these are electronic events, and so any gamma ray activity is a background for us. But we could do beryllium-7 at 2%, and this is actually close to what we have now. It's only a factor of 50% or so. But we could measure the CNO to 15%. And this is really what we would be after. And a measurement with this sensitivity could definitely distinguish between the metallicities, high or low. And it would be done basically at no cost. I mean, we would still design the cleanest experiment we can make with the lowest argon-39 we can have, And so this would be a measurement that wouldn't cost anything more, but it would definitely provide a lot of depth in the physics of the experiment for groups to jump on. Last slide, I serendipitously was on an email list at UMass, where it's in my institution, that on Monday they are having I turned it around here, but a celebration of US-Mexico scholarly exchanges. And UMass had a huge role in this millimeter telescope that is running now in Mexico. And this was the driver, and so most of the people here are astronomers. But I told them I would actually sneak in, not give a talk, but be there. And you know, we have our chancellor, and we have people from both the hard sciences and the social sciences. This is an interesting event that I will bring this meeting, and having met you all, and being now a collaborator with Eric too, to say, you know, there's more than this. There might be experiments with liquid argon as well. So anyway, in summary, Borg-Xeno now has a 10-year history of measuring neutrinos better and better. We have made milestone detections of the beryllium-7 flux and the PP flux and the PEP flux. We have set competitive limits on the CNO. We hope to maybe be making a measurement soon. There's plans on how to improve the detector. These depend on patients and plans for the experiment. SOX should happen. I hope it happens in the near future, searching for sterile neutrinos or putting a lid on the controversies. But by and large, I would say that the low background techniques that we developed have really spread out into the community in most experiments that are doing low event physics nowadays, and have really set a new standard of what one can do in terms of low radioactivity techniques. And one of the experiments that certainly has benefited is dark side, that now has expanded into a larger global collaboration to search for WIMPs and possibly to search for neutrinos from the sun. So I thank you for your attention again.
Thank you, very interesting talk. So we have again time for many questions.
So I have a few questions. On their side, to obtain the nuclear recoil region, do you discriminate, separate single and multiple scatters, or it's a full analysis?
We do separate. I mean, the multiple scatters are tagged as background. Yes.
They are tagged.
Yes.
And so you do that. How do you do that?
Well, I mean, a single site event is actually a double event. It's an S1 and then S2. So we require all events that go into that F90 against energy plot to have a clean S1 and a clean S2.
Yeah.
If there's anything missing or above that, we label it. And of course, we have categorized this with our source calibration campaigns, and it's much easier said than done. I mean, for example, my student is working on, is there a way to produce what looks like an S1 and S2 that looks legitimate by just pile up of spurious things, like an S2 without an S1 that couples to an S1 that doesn't have enough charge to generate an S2, for example, things like that. So we're looking at all of this in gory detail. It's a blind analysis, so we do this on all the open data. And then we have sidebands that we will be opening soon, again, to test the predictions of these models in the sideband and see if they match. Most interestingly, the biggest background we have is Cherenkov related. Cherenkov is light that is very fast. It has nothing to do with the physics of argon. It's produced in the plastics. It's produced everywhere, but in the plastics it can come out. And we have, not just a plastic, we also have a quartz window and the window of the PMTs. But the dangerous one is we have a reflector of Teflon on the sides, and we have light detectors, PMTs and dark side 50 above and below. And Cherenkov light produced in this Teflon actually has a very high F90. F90 is a measure of what fraction of your light pulse comes in a very short time at the beginning of the pulse. So if most of your light is at the beginning, that will be up in the plot.
So that topology cannot be easily removed.
Exactly, and so we're studying that in detail. The Cherenkov from the PMTs and the two quartz plates is easy because those events are very close to one given PMT. And so you measure the ratio of light in one PMT against all the others, and you see that it's very localized, very close to one PMT. And then there you do a cut. But those who are halfway through spread light around. And so the reason we haven't unblinded yet is we're understanding that.
And in Borexino, for all the neutrinos from supernova, you will get like 250 or so, something like that, right?
Depending on how far it is, obviously, but yes.
Yeah, but
that's at the standard distance.
Yes, and what is the time window for those events that you estimated? I'm thinking just how the 78 neutrinos.
We're talking about a few tens of seconds.
Yes, okay, that then it doesn't matter for the...
It doesn't matter, and it doesn't even matter for SOX.
Yeah.
Yeah.
And then the last one, just on the side to pick between the CNO neutrinos or SOX. So it cannot be
pushed
forward. So you're like confident that once SOX is done, you can return the detector to the current state to do CNO?
Okay, you want my opinion? I'm not confident at all, for a number of reasons.
Confident on...
I'm not confident that we can do it after SOX.
Yes.
I think if SOX happens for the solar program, probably that's it.
Okay,
unless you purify, but then that means going another 5 years or 3 years, because by the time you purify, you let it settle, you're talking about 5 years. And I think we're running into who's going to do it. Now, collaborators are doing other things now, me included. And if SOX runs, it means we've calibrated before. We've inserted sources in. And at the level of a few counts of bismuth per 100 tons per day, we most certainly will have, well, most certainly. I think that we will have introduced that kind of radioactivity by calibrating.
But now that you understand the polonium-210 and it's just a few months, right, that you have this clean new area, how long does it take to do?
I think if we had 6 months, we would do it. 6 months. And if in those 6 months the stability that we've observed continues, because of course if at some point things mix up again, then that then we have to start over.
Should probably stop giving them ideas for CNO, right?
Yeah, I mean, I was talking to Mark about this possibility in Snow Plus, and to some extent, Snow Plus is leaning on the rock, and so it's thermally much more stable. I mean, the periphery of Snow Plus is equilibrated to the rock. We had this air in the hall that changed temperature all the time. And so probably even just the stability, even in presence of background, of the detector is much better. But you have to let it settle after the filling, which when you fill it, it's distilled, it's warmer, it has to cool down to whatever the temperature is. And in those months, you will have probably some motion. I expect. And so how long Snow Plus would have to run to do this, I don't know.
More questions?
I hope they can do it.
I have a question the question is, can argon be sensible to either the axioelectric effect or effect from other exotic dark matter particles candidates?
So the axioelectric effect I see hard because of we rely I mean, certainly in principle, I mean, there would be if that effect exists, we would have those in the data set. Whether we would be able to disentangle those from other electron-like events, probably not. But I would have to look at the rates and the numbers that are interesting. But I highly suspect that we wouldn't say anything interesting. Other WIMP-like things or dark matter candidates, it depends on their interaction mode. You know, so the sensitivity curves we present are those based on fully taking advantage of the discrimination between the nuclear recoils and the electron recoils. And so for that, you either have something that recoils with the nucleus or that particular sensitivity does not apply. Obviously, once we will hopefully have an experiment, you also do other searches. So the xenon experiments, for example, try to push down the threshold by looking at S2 only events. So they look for, and for that, they in principle have single electron sensitivity, which means that they see single electron events. Whether those single electrons are very low energy scatterings of electrons of some leptophilic WIMP, or they're just instrumental effects where you have some evaporation of electrons at the surface of the liquid to gas transition. This I don't know. And in fact, the trigger rate on those is high enough that I'm sure that they're dominated by an instrumental effect, and whether they can understand it enough to disentangle things. And of course, we in Argon will try to do that, but we don't promise it because we don't really know the performance of a detector ahead of time in that arena, which starts being a very, you move a parameter a little bit in the detector and your sensitivity just changes orders of magnitude. And so we'll see. When we run the detector, we'll do all the physics we can do with it. But we don't sell the detector to doing that.
Thank you. Sorry, I have another question.
Yeah.
Please. In the context of the neutrino floor in the dark matter detection, there have been efforts either on Barksino or other neutrino experiment to determine where to determine the direction of where neutrinos come from in order to...
So directionality you're asking about, and whether existing experiments have looked for dark matter. I mean, every experiment has looked for whatever they can look for. Barksino specifically is not sensitive to these very low energy recoils because the carbon-14 just kicks in. And so even if we have them, they would be buried in there. So liquid scintillator is probably not the medium of choice to do these experiments at very, very low energy. But other neutrino experiments have looked for indirect detections, like signatures of high energy gamma rays of annihilation of WIMPs in the sun or other places, and then you can set some limits. Barksino is almost too small to do that. I mean, these are carried out by experiments, possibly Super K has looked into this, but like IceCube, or where you really need these enormous targets to do it. Or satellites in space. Gamma ray satellites like Fermi certainly has looked for this type of indirect detection, or AMS has looked for positrons, and there's interesting anomalies, excesses of particles that are still not completely explained and ruled out. Now there's a very active field of R&D now that WIMPs are not being found, where the standard SUSY would have told you to look for. There's a very interesting set of ideas of detectors that can really push the thresholds to low thresholds. And some of them have motivations in theory of some models. Some actually don't. The dark photon, yes, there's certainly a lot of theory that can incorporate a dark photon, But by and large, a lot of people have said, well, I can go and look for these kind of things, and we can build an experiment to do that. And there's a flurry of beautiful experimental techniques at accelerators and of this kind with superfluid helium, with CCDs, which are going to happen in the next 1 to 3 decades, I suspect.
Thank you so much for the explanation.
More questions?
You mentioned electron decay.
Yes.
Was that process charge violating process?
Yes.
And so, which theory predicts that?
Well, I said that this is really theoretically not motivated in any way because it really collapses the foundations of field theory.
Nothing is sacred.
But Okun has introduced this I think in the 60s. I think it's Lev Okun who started talking about this. And I think there is a particular charm. I mean, you wouldn't build an experiment this expensive to do it only. So you build either very small experiments that don't cost much and do it, or they're parasitic things that you can look into and then you report that you haven't found it in this case. But the fundamental violation of fundamental symmetries of nature, charge violation, mass violation, or energy non-conservation, or the violation of the Pauli principle, which is being looked at by some of these experiments by sort of things disappearing and emitting radiation and that you detect. There's a fascination of, well, I'll look. I don't really hold my breath about it, but obviously, one has to tread very carefully because the opera experiment has taught us not to be too overly enthusiastic about these kind of violations. But looking for them, I think, is natural curiosity of humanity, I think. So, we have a theory that's very beautiful, and it stands on pillars which are hard to demolish. But the neutrino, Bohr was ready to give up conservation of energy. What was it theoretically founded? No. Actually, in fact, it would have been a disaster for all of theory, pretty much. But I think there's nothing wrong in looking for them.
More questions? So we thank again Andrea for his is